There exists a world in our cosmic neighborhood where 1 year lasts an entire human lifetime. A frozen giant that rolls through space like a cosmic marble, tilted so dramatically on its axis that it doesn't spin like a top, but tumbles sideways through the darkness. For 42 years, one hemisphere basks in continuous sunlight, while the opposite pole languishes in unbroken night. Then, as if following some ancient choreography written into the fabric of space itself, the roles reverse for another 42 years. This is Uranus, the ice giant that defies every expectation we hold about how planets should behave. Tonight, as you settle into comfort and let the day's concerns drift away, we're embarking on a journey to this enigmatic world, exploring how it came to sleep through decades of darkness and what secrets lie beneath its serene, cyan surface. So why does this distant giant appear to slumber for 42 years at a time? And what cosmic catastrophe sentenced it to such an unusual fate? Before we begin, I'd love to know where you're listening from tonight and what time it is in your corner of the world. Drop your location in the comments and join this global community of curious minds exploring the cosmos together. Let us start not with Uranus itself, but with a delicate dance of light. Imagine standing in a field on a clear night, looking up at the stars scattered across the velvet darkness. To the ancients, these points of light were fixed, eternal, unchanging. They mapped the heavens with careful observations, noting 5 wandering stars that moved against the celestial backdrop: Mercury, Venus, Mars, Jupiter, Saturn. For thousands of years, these 5 wanderers constituted the entirety of humanity's known planets. The universe, it seemed, had revealed all its planetary secrets, but the cosmos is rarely so obliging. On the night of March 13th, 1781, a German-born musician turned astronomer named William Herschel stood in the back garden of his home at 19 New King Street in Bath, England. The air was cool, the sky remarkably clear. Herschel had been systematically surveying the heavens with a homemade telescope, cataloguing every star down to the 8th magnitude of brightness. It was meticulous work, the kind that required patience, precision, and an almost meditative focus. Between 10 and 11 o'clock that evening, while examining the region near the star Zeta Tauri in the constellation Gemini, Herschel noticed something peculiar. In his journal, he wrote with characteristic scientific caution that he had observed either a nebulous star or perhaps a comet. 4 nights later, on March the 17th, he turned his telescope toward the same patch of sky and immediately recognized that the object had moved relative to the background stars. This was no fixed stellar light. Herschel noted with growing excitement that he had found a comet, for it had changed its place. But comets, those icy visitors from the outer reaches of the solar system, typically display long streaming tails of gas and dust as they approach the sun. This object possessed no such tail. Its appearance was that of a well-defined disk, sharp-edged and solid-looking. Over the following weeks and months, astronomers across Europe directed their instruments toward Herschel's discovery. Russian academician Anders Lexell computed the object's orbit and arrived at a startling conclusion. This was no comet tracing an elongated ellipse through the inner solar system. The orbit was nearly circular, lying far beyond Saturn. German astronomer Johann Elert Bode described it as a moving object that could be deemed a previously unknown planet-like body circulating beyond the orbit of Saturn. by 1783, Herschel acknowledged to the Royal Society that by observation of the most eminent astronomers in Europe, it appeared that the new star he had pointed out in March 1781 was in fact a primary planet of our solar system. The discovery was nothing short of revolutionary. For the first time in recorded history, humanity had expanded the known boundaries of the solar system. The universe was larger than anyone had imagined. Herschel, ever the loyal subject, initially proposed naming his discovery Georgium Sidus, or George's Star, in honor of King George III. The gesture earned him royal patronage and the position of court astronomer, along with a generous annual stipend that allowed him to abandon his musical career and dedicate himself entirely to astronomy. But the name Georgium Sidus did not sit well with astronomers beyond Britain's shores. In France, where reference to the British monarchy was distinctly unwelcome, the planet was often called simply Herschel. Johann Bode, recognizing the need for a name that followed the mythological pattern of other planets, proposed Uranus after the Greek god of the sky. In classical mythology, Uranus was the father of Cronus, known to the Romans as Saturn, and grandfather of Zeus, or Jupiter. The name maintained the celestial genealogy and, uniquely among the planets, retained its Greek rather than Roman form. By the early 19th century, Uranus had become the universally accepted name for the solar system's seventh planet. Herschel's discovery had effectively doubled the known size of the solar system in a single observation. Saturn, long considered the outermost sentinel of the Sun's domain, suddenly had a distant companion orbiting nearly twice as far from our star. The universe had whispered a secret to patient observers, and nothing would ever quite be the same. Now let us journey outward from our Earth, crossing the vast distances that separate us from this ice giant. Uranus orbits the Sun at an average distance of about 19 times the Earth-Sun separation. To put this in perspective, if you could somehow drive a car at highway speeds toward Uranus, the journey would take more than 2,000 years of continuous travel. Light itself, racing at nearly 300,000 kilometers per second, requires approximately 2 hours and 40 minutes to traverse the gulf between the Sun and Uranus. This immense distance creates a realm of perpetual twilight where sunlight, though still present, arrives with less than 1/400th the intensity we experience on Earth. The Sun from Uranus would appear as a brilliant point of light, far brighter than any star, yet offering little warmth to the frozen world it illuminates. The planet completes one orbit around the Sun every 84.02 Earth years. Think about that for a moment. A single Uranian year spans nearly a human lifetime. When Herschel discovered Uranus in 1781, the planet would not complete even one full orbit around the Sun until 1865. By the time it returned to that same position again, it was 1949. The next time Uranus completes an orbit from its discovery point will be 2033, more than 2.5 centuries after human eyes first recognized it as a world rather than a star. But it is not merely the planet's distance or its leisurely orbital period that makes Uranus extraordinary. It is the way it moves through space, the peculiar geometry of its existence. Most planets in our solar system spin with their axes roughly perpendicular to their orbital planes, like tops spinning on a table. Their poles point up and down relative to the flat disk in which they orbit the Sun. Earth's axis tilts at 23.5 degrees, giving us our seasons as different hemispheres tip toward or away from the Sun during our yearly journey. Saturn tilts at about 27 degrees. Even Jupiter, that massive gas giant, maintains a relatively upright posture with only a 3-degree tilt. But Uranus lies on its side. Its rotational axis tilts at an astonishing 98 degrees to its orbital plane, meaning it essentially rolls around the Sun like a ball rolling along the ground. The planet doesn't spin, it tumbles. Imagine a world where the North Pole points directly at the Sun for decades, bathing one entire hemisphere in endless daylight, while the opposite hemisphere experiences an equally endless night. Then, 42 Earth years later, as Uranus continues its orbit, the poles trade places. The hemisphere that knew only darkness begins its long summer, while the one that basked in sunlight enters its extended winter. At the equator, the experience is dramatically different. Near the times when the Sun shines over Uranus's equator, at what we call the planet's equinoxes, the equatorial regions experience something closer to normal day-night cycles. The planet rotates once every 17 hours and 14 minutes, meaning each Uranian day passes slightly faster than an Earth day. But this respite is temporary. As the planet continues its orbit and one pole once again tips toward the Sun, the equatorial regions enter a long period where the Sun traces a low arc across the sky, never climbing far above the horizon. The consequences of this extreme axial tilt are profound. At the poles, residents, were any to exist, would witness the Sun spiral slowly higher in the sky over the course of 21 years, reaching its zenith at the summer solstice, before beginning an equally slow descent back toward the horizon over another 21 years. Once the sun set, 42 years of darkness would follow before the next sunrise. It's a world of extremes, of patience, measured not in days or weeks, but in decades. The Uranian seasons are marathons, not sprints. This strange orientation almost certainly resulted from a catastrophic collision early in the planet's history. Computer models suggest that roughly 4 billion years ago, when the solar system was still young and chaotic, a massive protoplanet, perhaps as large as Earth, smashed into the young Uranus. The impact was violent enough to knock the planet onto its side while leaving it otherwise intact. Some theories propose that Uranus once possessed a massive moon whose gravitational influence gradually destabilized the planet's rotation before the moon itself crashed back into its parent world. Other models suggest that gravitational interactions between the giant planets during the solar system's formative years may have torqued Uranus into its current orientation through resonant forces acting over millions of years. Whatever the cause, this ancient catastrophe fundamentally altered Uranus's character, transforming it into the cosmic oddity we observe today. Uranus appears to telescopes as a pale blue-green disk, serene and nearly featureless. The color derives from methane in its upper atmosphere, which absorbs red wavelengths of sunlight and reflects blue and green back into space. When Voyager 2, humanity's only spacecraft to visit Uranus, flew past the planet in January 1986, it captured images of what appeared to be a bland, almost boring world. The photographs showed a nearly uniform cyan sphere with barely any visible cloud features storms, or atmospheric bands. To scientists accustomed to the dramatic beauty of Jupiter's swirling storms and Saturn's elegant bands and vortices, Uranus seemed disappointingly quiet. But this apparent blandness masks a complex and dynamic world. The planet's atmosphere is primarily hydrogen and helium, similar to Jupiter and Saturn, but with a significantly higher proportion of what astronomers call ices. These aren't ices in the familiar sense of frozen water. Instead, the term refers to volatile compounds, water, methane, and ammonia that exist in various exotic states under the extreme pressures and temperatures deep within the planet. Near the cloud tops, methane gas accounts for about 2 to 3% of the atmosphere by volume, roughly 20 to 30 times more abundant than in the Sun. Below this lies a complex layered structure where pressures and temperatures climb steadily with depth. Uranus has the coldest planetary atmosphere in the solar system, with minimum temperatures plunging to 49 Kelvin, or minus 224 degrees Celsius. That's colder than Neptune, despite Neptune being farther from the Sun. The reason for this extreme cold is puzzling. Unlike Jupiter, Saturn, and Neptune, which all radiate more heat into space than they receive from the Sun, Uranus appears to have very little internal heat. Most planets generate internal warmth through gradual gravitational contraction, or, in the case of the gas giants, through exotic processes involving metallic hydrogen in their cores. But Uranus radiates almost no excess heat. One hypothesis suggests that the same catastrophic impact that knocked Uranus onto its side may have also disrupted its internal structure, preventing efficient heat flow from the core to the surface. Another possibility involves the planet's layered interior. Recent research suggests that the extreme pressures deep within Uranus may cause the water, methane, and ammonia in its interior to separate into immiscible layers, much like oil and water. This stratification could prevent convection, trapping heat deep within the planet and leaving the upper atmosphere frigidly cold. The result of this cold, relatively stable atmosphere is the featureless appearance that puzzled early observers. Clouds on Uranus don't billow dramatically above the upper haze layers as they do on Jupiter and Saturn. Instead, they remain confined to lower altitudes, hidden beneath a thick methane fog that gives the planet its uniform appearance. But appearances, as we know, can be deceiving. When Voyager 2 visited in 1986, it happened to arrive during the Uranian Southern Hemisphere's summer solstice. The South Pole was pointed almost directly at the Sun, and the extreme temperature difference between the illuminated and dark hemispheres may have suppressed atmospheric activity. More recent observations using the Hubble Space Telescope and ground-based observatories have revealed that Uranus is far more dynamic than Voyager's images suggested. As the planet progressed toward its equinox in 2007, when the Sun shone over Uranus's equator for the first time in 42 years, telescopes began detecting dramatic atmospheric changes. Bright clouds appeared in the northern hemisphere, emerging from decades of darkness into sunlight. Dark storms comparable in size to North America materialized in the planet's atmosphere. Atmospheric bands became visible, shifting in size and brightness as sunlight reached latitudes that had been shrouded in winter's grip. Wind speeds on Uranus can reach up to 900 kilometers per hour, making them the second fastest in the solar system after Neptune. Near the equator, these winds blow in the retrograde direction, opposite to the planet's rotation. Closer to the poles, the wind patterns shift to prograde flow, moving with the planet's spin. The atmospheric dynamics are complex and still poorly understood, shaped by that extreme axial tilt and the resulting bizarre seasonal cycle. As the Northern Hemisphere continues its long approach towards summer solstice, in 2028, scientists are watching closely. A bright polar cap of photochemical haze has been growing over the North Pole, thickening year by year. This haze, which looks similar to smog over cities on Earth, forms when sunlight drives chemical reactions in the methane-rich atmosphere. The products of these reactions, hydrocarbons like ethane, acetylene, and other complex molecules, accumulate in the upper atmosphere, creating a bright crown over the illuminated pole. The South Pole, which knew continuous daylight when Voyager visited, has been darkening as it enters its decades-long winter, while the North Pole brightens with each passing year. Now we must venture deeper, beyond the visible clouds and into the hidden interior of this ice giant. Uranus's total mass equals about 14.5 times that of Earth, making it the least massive of the giant planets. Yet its diameter spans roughly 4 Earth diameters, making it the third largest planet in the solar system, after Jupiter and Saturn. This gives Uranus a relatively low density of about 1.27 grams per cubic centimeter, indicating a composition dominated by ices rather than the hydrogen and helium that comprise the gas giants. The current model of Uranus's internal structure envisions 3 distinct layers. At the very center lies a rocky core, composed primarily of silicate rocks and iron-nickel alloys. This core represents less than 20% of the planet's radius, but is incredibly dense, with pressures reaching 8 million bars, or 800 gigapascals, and temperatures climbing to about 5,000 Kelvin. Surrounding this rocky heart is a thick mantle that comprises the bulk of the planet's mass, approximately 60% of its total volume. This is where Uranus truly earns its designation as an ice giant. The mantle consists of a hot, dense, electrically conducting fluid containing water, ammonia, methane, and other volatiles. Under the extreme pressures deep within the planet, these materials exist in supercritical states, neither quite liquid nor quite gas, but something in between. This water-ammonia ocean, as it's sometimes called, may contain some of the most exotic chemistry in the solar system. Laboratory experiments and computer simulations suggest that the extreme conditions deep in Uranus's mantle may break apart methane molecules, allowing carbon atoms to crystallize into diamonds. Yes, diamonds. It's theorized that diamond hailstones may rain down through the mantle, like frozen precipitation, sinking toward the core mantle boundary. Some models even propose that an ocean of liquid metallic carbon, studded with floating diamond icebergs, may exist at the base of the mantle. These diamond seas, if they exist, would be utterly alien, existing under pressures and temperatures that transform familiar materials into exotic states of matter. Recent research has suggested that Uranus's interior may be even more methane-rich than previously assumed. Models that account for the organic-rich composition of objects in the outer solar system, where Uranus likely formed, indicate that methane could comprise more than 20% of the planet's interior mass. This high methane abundance may have resulted from chemical reactions that occurred during the planet's formation, as carbon-rich planetesimals collided with the growing world and reacted with hydrogen under intense heat and pressure. The outer layer of Uranus consists of a hydrogen and helium atmosphere extending down to where the increasing pressure gradually transitions the gases into liquid, then into the supercritical fluids of the mantle. There is no solid surface anywhere on Uranus, no place where a spacecraft could land. Any probe descending through the atmosphere would eventually be crushed by mounting pressure and seared by rising temperatures long before reaching anything resembling ground. One of the most puzzling aspects of Uranus's interior reveals itself through the planet's magnetic field. In 1986, when Voyager 2 measured Uranus's magnetosphere, scientists were shocked by what they found. Unlike Earth, where the magnetic field aligns relatively closely with the planet's rotational axis, Uranus's magnetic field tilts at a staggering 59 degrees from its spin axis. Moreover, the field doesn't originate from the planet's center, but is offset by about 30% of Uranus's radius. The magnetic field tumbles wildly as the planet rotates, creating a chaotic and unpredictable magnetosphere. Neptune, the other ice giant, displays a similarly tilted and offset magnetic field, leading scientists to conclude that something fundamentally different must be happening inside ice giants compared to Earth or the gas giants. The prevailing theory suggests that Uranus's magnetic field is generated not deep in its core, as Earth's is, but at relatively shallow depths in the water-ammonia ocean of the mantle. The high electrical conductivity of this layer, combined with the planet's rotation, creates a dynamo effect that generates the magnetic field. But the stratified, possibly immiscible layers within the planet prevent large-scale convection, resulting in a multipolar field structure rather than the simple dipole field characteristic of Earth. This unusual magnetic field has significant consequences for Uranus's magnetosphere, the protective bubble of magnetic influence that surrounds the planet. Earth's magnetosphere does a relatively good job of shielding our planet from the solar wind, the stream of charged particles constantly flowing from the sun. But Uranus's misaligned, offset magnetic field creates a magnetosphere that changes drastically with the intensity of the solar wind. This brings us to one of the most significant recent discoveries about Uranus, a finding that fundamentally changed our understanding of the planet and revealed just how unusual Voyager 2's brief visit actually was. For nearly 4 decades, scientists puzzled over the Voyager data. The magnetosphere Voyager measured seemed unusually empty, devoid of the hot plasma that populates the magnetospheres of Jupiter and Saturn. This was particularly strange because 5 of Uranus's icy moons orbit within the magnetosphere, and these moons should have been ejecting ions into the surrounding space through various processes. The lack of plasma led scientists to conclude that the moons must be entirely inactive, geologically dead worlds incapable of contributing material to their environment. The radiation belts detected by Voyager were also surprisingly intense, adding another layer to the mystery. Then, in 2024, researchers took a fresh look at the Voyager 2 data. They discovered something remarkable. Just days before Voyager's encounter with Uranus, an intense burst of solar wind was released from the Sun. This pressure wave from our star traveled outward through the solar system and slammed into Uranus, shortly before Voyager arrived. The solar wind compressed Uranus's magnetosphere dramatically, likely pushing plasma out of it and creating the empty conditions Voyager observed. The solar wind also fed electrons into the magnetosphere, boosting the radiation belts to the intense levels detected by the spacecraft. In essence, Voyager visited Uranus at one of the most unusual times possible. The spacecraft observed the planet during a rare cosmic anomaly, not during its normal state. Scientists now believe that on a typical day, Uranus's magnetosphere likely contains plasma from its moons, and the radiation belts are less intense. The picture of Uranus as a bland, inactive system with geologically dead moons may need to be completely rewritten. The discovery underscores an important lesson about planetary exploration. A brief flyby, even one as successful as Voyager 2's, captures only a snapshot in time. Planets are dynamic, changing systems, and understanding them fully requires long-term observation, or, ideally, an orbiter that can study the planet through different seasons and solar conditions. It also raises exciting possibilities about Uranus's moons. If they are indeed active enough to contribute material to the magnetosphere, then perhaps they harbor subsurface oceans or geological processes that could make them far more interesting than anyone previously imagined. Speaking of moons, let us turn our attention to the family of satellites that accompany Uranus on its journey around the Sun. As of late 2025, astronomers have confirmed 29 moons orbiting the ice giant, and there are likely more waiting to be discovered in the coming years. These moons fall into three distinct groups. The innermost moons are small, dark bodies that share common properties with Uranus's ring system. Many were discovered by Voyager 2 and are tiny, irregular objects shepherding the rings and sweeping up debris. Then come the 5 major moons, discovered telescopically from Earth between 1787 and 1948. These are the crown jewels of the Uranian system: Miranda, Ariel, Umbriel, Titania, and Oberon. They range in diameter from 472 kilometers for Miranda to 1,578 kilometers for Titania. All 5 moons orbit in Uranus's equatorial plane, meaning they too are tilted on their sides, experiencing the same extreme seasonal cycle as the planet itself. Finally, the irregular moons orbit at great distances on highly inclined, often retrograde orbits. These are likely captured asteroids or Kuiper belt objects, snagged by Uranus's gravity at some point in the distant past. Uniquely among the solar system's planets, Uranus's moons are named after characters from English literature rather than classical mythology. The tradition began with William Herschel's son, John Herschel, who suggested names drawn from the works of William Shakespeare and Alexander Pope. Oberon and Titania, the largest moons, are the fairy king and queen from Shakespeare's A Midsummer Night's Dream. Ariel appears as a spirit in The Tempest, while Miranda, the smallest of the 5 major moons, is named after the innocent heroine of The Tempest. Subsequent discoveries have continued this literary tradition, giving us moons named Puck, Ophelia, Cordelia, Desdemona, Juliet, Portia, and many others, creating a celestial cast of Shakespearean characters orbiting the ice giant. The 5 major moons are thought to have formed from an accretion disk around Uranus, either during the planet's original formation or possibly from debris kicked up by the massive impact that tilted the planet. They are composed of roughly equal parts water ice and rocky material, making them similar in some ways to the moons of Saturn. However, their surfaces are considerably darker, with reflectivity ranging from 30 to 50%. Umbriel is the darkest of the five, while Ariel is the brightest. The surfaces of these moons tell stories of complex geological histories. All of them, except Umbriel, show signs of past geological activity in the form of canyons, scarps, and other features indicating that their interiors were once warmed enough to drive tectonic processes. Ariel appears to have the youngest surface, with relatively few large impact craters, suggesting that geological activity erased older craters relatively recently in astronomical terms. Its surface displays intersecting valleys and smooth regions that may have been resurfaced by water or ammonia-rich fluids welling up from the interior. Titania, the largest Uranian moon, displays an ancient heavily cratered surface crisscrossed by enormous fault canyons. Some of these canyons stretch hundreds of kilometers across the moon's face, suggesting that Titania underwent significant expansion at some point in its past, possibly as its interior froze and expanded, cracking the surface. Oberon, the outermost large moon, appears ancient and inactive, its surface saturated with impact craters. A mysterious bright ray system radiates from one side of the moon, possibly indicating a relatively recent large impact that exposed fresh ice beneath the dark surface material. Umbriel, true to its name, derived from a dark, melancholic spirit in Pope's poem, is the darkest of the major moons. Its surface shows little evidence of recent activity and is heavily cratered, suggesting it has remained geologically quiet for billions of years. But then there is Miranda, and Miranda is unlike anything else in the solar system. When Voyager 2 captured detailed images of this small moon in 1986, planetary scientists were stunned. Miranda's surface appears to be a chaotic patchwork of wildly different terrains jammed together with no apparent logic. There are ancient, heavily cratered regions that look billions of years old. Right next to them are strange ovoid features called coronae, racetrack-shaped structures of parallel ridges and grooves that look almost artificially carved. Enormous fault scarps cut across the surface, some reaching depths 12 times greater than the Grand Canyon. The surface looks as if Miranda was shattered into pieces and then reassembled randomly, earning it the nickname the Frankenstein Moon. The origin of Miranda's bizarre appearance remains hotly debated. One early hypothesis suggested that Miranda was indeed broken apart by a massive impact and then reformed from the fragments. However, this idea has fallen out of favor. The current leading theory involves tidal heating. In the past, Miranda may have been locked in orbital resonances with other Uranian moons, particularly Umbriel. These resonances would have forced Miranda's orbit to become more elliptical, causing the moon to flex and heat up from tidal forces as its distance from Uranus varied. This internal heating could have driven intense geological activity, creating the coronae and other young-looking features. When the resonance eventually broke, perhaps through interactions with other moons, the heating stopped, and Miranda froze solid with its strange surface features preserved. Exciting new research suggests that several of Uranus's major moons may harbor subsurface oceans. Computer models accounting for the moon's compositions, the heat generated by radioactive decay in their rocky cores, and the insulating properties of their surfaces indicate that liquid water could persist beneath the icy crusts of Ariel, Umbriel, Titania, and Oberon. These oceans would likely be relatively thin, perhaps less than 30 kilometers deep in Ariel and Umbriel, and up to 50 kilometers in Titania and Oberon. But they would be oceans nonetheless. The presence of salts and ammonia in these putative oceans would act as antifreeze, keeping the water liquid even at temperatures below the normal freezing point. Titania and Oberon's oceans might even be warm enough at the core mantle boundary to potentially support habitability, though this remains highly speculative. Miranda, unfortunately, is probably too small to have retained sufficient internal heat, and any ocean it might once have possessed has likely frozen solid. In August 2025, astronomers using the James Webb Space Telescope announced the discovery of Uranus's 29th moon, designated S2025-U1. This tiny satellite, measuring only about 10 kilometers in diameter, orbits between the moons Ophelia and Bianca at a distance of approximately 56,000 kilometers from Uranus's center. Its circular orbit suggests it formed near its current location, rather than being a captured object. The moon's small size likely explains why Voyager 2 missed it during its flyby nearly 40 years earlier. The discovery demonstrates the extraordinary capabilities of Webb's infrared instruments and suggests that more small moons await discovery in the Uranian system. Some planetary scientists believe there could be dozens of tiny moonlets shepherding the rings and lurking in the spaces between the known satellites. Each discovery adds another piece to the puzzle of how this complex system formed and evolved over billions of years. Now we come to one of Uranus's most beautiful and enigmatic features, its ring system. Before 1977, Saturn was the only planet known to possess rings, and its magnificent, broad ring system had been observed through telescopes since Galileo's time. The idea that other planets might also have rings was purely speculative. That changed on March 10th, 1977, when astronomers James Elliott, Edward Dunham, and Jessica Mink were flying aboard NASA's Kuiper Airborne Observatory, an airplane equipped with an infrared telescope. They were preparing to observe a stellar occultation, an event where Uranus would pass in front of a distant star designated SAO 158687. By watching how the star's light dimmed as it passed behind Uranus's atmosphere, they hoped to learn about the planet's atmospheric structure. What happened next was completely unexpected. As they monitored the star's brightness, it suddenly dimmed, not once but 5 times in quick succession, well before Uranus itself blocked the star. Then, after Uranus had passed and the star should have been visible again, the pattern repeated in reverse. 5 brief dips in brightness, mirror images of the dips observed before the occultation. The spacing of the dips on one side of Uranus matched exactly the spacing on the other side. There could be only one explanation. Uranus was surrounded by rings. The discovery electrified the astronomical community. Subsequent observations from multiple sites revealed additional rings, bringing the initial count to 9. These weren't broad, bright rings like Saturn's. The Uranian rings were narrow, sharp-edged, and extraordinarily dark, reflecting only a few % of the sunlight that struck them. When Voyager 2 arrived at Uranus in January 1986, it confirmed the rings and discovered 2 more. bringing the total to 11. The spacecraft's cameras captured stunning images of the ring system backlit by the sun, revealing not just the main rings, but also faint dust bands distributed between them. These wispy dust lanes appeared brighter in forward scattered light, indicating they contained microscopic particles along with the larger chunks of material making up the main rings. In 2003 and 2005, the Hubble Space Telescope detected 2 additional outer rings, bringing the count to 13. These outer rings are quite different from the narrow inner rings. They are broader, more diffuse, and one of them, the Mu ring, is distinctly blue in color, similar to Saturn's E ring. The blue color suggests the ring is composed primarily of small icy particles that scatter blue light more efficiently than red. As currently understood, Uranus's ring system comprises 3 groups: 9 narrow main rings, labeled with numbers and Greek letters: 6, 5, 4, alpha, beta, eta, gamma, delta, and epsilon; 2 dusty rings, the zeta ring and lambda ring; and 2 outer rings, the Nu ring and the Mo ring. The rings orbit Uranus in its equatorial plane, meaning they too are tilted dramatically relative to the planet's orbit. The rings' orbits range from about 38,000 kilometers from Uranus for the innermost Zeta ring to about 98,000 kilometers for the outermost Mu ring. The composition of the Uranian rings is unusual. Unlike Saturn's rings, which are predominantly water ice and thus quite bright, Uranus's rings are among the darkest objects in the solar system. Spectroscopic observations suggest they're made primarily of water ice mixed with dark organic compounds created when radiation from space strikes methane and other carbon-bearing molecules. This radiation processing gradually darkens ice over time, giving the rings their charcoal-like appearance. The particles making up the rings range in size from fine dust to boulders several meters across. Most of the mass in the main rings is in larger particles, objects greater than about 1 meter in diameter. The dust component appears to be continually produced by collisions between larger particles and may also be generated by micrometeorite impacts on the small moons orbiting near the rings. The lifetime of dust particles orbiting Uranus is quite short, perhaps only a few thousand years, because they are gradually dragged down into the planet's atmosphere by atmospheric drag and pushed by radiation pressure from sunlight. This means the dust we see today must be continuously replenished. The main rings themselves may also be relatively young in astronomical terms, perhaps only a few 100 million years old, rather than dating back to the solar system's formation 4.6 billion years ago. The narrow, sharp-edged structure of the main rings poses a significant dynamical puzzle. Without some mechanism to confine them, collisions between ring particles would naturally cause the rings to spread out radially, becoming broader and more diffuse over time. For several of the rings, astronomers have identified shepherd moons, small satellites orbiting just inside or outside the rings, whose gravitational influence herds the ring particles and prevents spreading. The most famous shepherd pair consists of the moons Cordelia and Ophelia, which bracket the Epsilon ring, the brightest and most massive of the Uranian rings. Resonances between the rings and these moons create regions where ring particles cannot stably orbit, effectively defining the ring's inner and outer edges. However, not all the rings have identified shepherds, and how they maintain their narrow structure remains an open question. Some researchers propose that unseen moonlets, too small to have been detected, but large enough to gravitationally influence the rings, may be embedded within the ring system. Others suggest that the rings may simply be young enough that they haven't had time to spread significantly. Still others propose more exotic mechanisms involving the self-gravitational wakes of ring particles or electromagnetic effects in the dusty portions of the rings. When viewed from Earth, Uranus's rings change their appearance dramatically over the course of the planet's 84-year orbit. At equinox, when the sun shines over Uranus's equator, we see the rings edge on, and they can become almost invisible, reduced to a thin line even in powerful telescopes. At solstice, when one of Uranus's poles points toward the sun and Earth, we see the rings more face-on, and their structure becomes visible. The Mu ring, discovered during a favorable viewing geometry near Uranus's equinox, exemplifies how much remains to be discovered. The rings themselves cast shadows on Uranus's atmosphere during certain parts of its orbit, creating dark bands that move across the planet as it rotates. These shadows may influence atmospheric temperatures and circulation patterns, adding yet another layer of complexity to the interconnected Uranian system. As we drift deeper into this exploration, let us return to the question posed at the beginning of our journey. Why does Uranus sleep for 42 years at a time? What does this strange slumber mean for the world itself? The answer lies in that catastrophic tilt, that 98-degree lean that makes Uranus roll rather than spin. During the Uranian winter at any given pole, that hemisphere points away from the sun, plunging into darkness for 42 years. With no sunlight to drive photochemistry, warm the atmosphere, or power weather systems, the entire hemisphere enters a kind of hibernation. The atmosphere cools, methane and other volatiles condense and settle. The polar regions become vast frozen reservoirs of dormant chemistry. Then comes the solstice, when the sun shines directly over one pole. That entire hemisphere awakens. Sunlight pours onto regions that have known only darkness for decades. The sudden energy input drives photochemistry, creating complex hydrocarbons that accumulate in the upper atmosphere, forming the bright polar cap seen in recent observations. Atmospheric circulation patterns shift as temperature gradients develop between the illuminated and dark hemispheres. Storms form, winds accelerate, the planet comes alive. But this awakening is slow and gradual, measured in years and decades rather than days or weeks. The thick atmosphere of Uranus responds sluggishly to seasonal forcing, and the lack of significant internal heat means there's no internal energy reservoir to accelerate changes. The planet sleeps through its long winter night, then slowly, almost reluctantly, awakens to its brief summer. Recent observations have given us unprecedented views of this seasonal transformation. As Uranus approaches northern summer solstice in 2028, the North Polar region has been brightening steadily for years. The atmospheric haze cap grows thicker and more prominent with each passing year. Cloud activity has increased dramatically in the northern hemisphere, with bright features appearing at latitudes that were dark and featureless during Voyager's visit. Scientists are watching closely, documenting the awakening of a hemisphere that has been emerging from 4 decades of darkness. The South Pole, conversely, is entering its long sleep. The bright features visible in Voyager's images have faded. The polar region is darkening as sunlight retreats. Over the coming decades, the entire southern hemisphere will cool and quiet, entering the dormant phase that the north is now leaving behind. This seasonal cycle affects more than just the atmosphere. Recent studies suggest that the extreme seasons may influence Uranus's auroras. On Earth, auroras occur when charged particles from the Sun follow magnetic field lines to the polar regions, where they collide with atmospheric atoms and molecules, causing them to glow. The aurora form rings around Earth's magnetic poles. On Uranus, the extreme tilt means that the ESR magnetic poles, which are already offset from the rotational poles by nearly 60 degrees, sometimes point directly at the Sun for extended periods. This creates a unique situation where the solar wind can have direct access to high-latitude regions, potentially creating auroras at unusual locations. Voyager detected signatures of auroras during its flyby, but observations from ground-based and space telescopes have revealed even more unusual behavior. Uranus's auroras don't form stable rings or ovals around the poles. Instead, they appear as bright spots that flicker and move rapidly across the planet, sometimes appearing near the equator rather than the poles. The chaotic nature of Uranus's magnetosphere, combined with its extreme seasons, creates auroral displays unlike anything else in the solar system. The rings and moons also respond to the seasonal cycle. The shepherd moons experience changing illumination conditions as the system orbits the Sun. When we view the rings edge-on, solar heating of the ring particles is minimal. When we see them more face-on, the Sun's rays strike them more directly, potentially causing temperature changes that might affect particle dynamics. The moons themselves undergo extreme seasonal variations. During each moon's winter, one hemisphere remains in darkness for decades. Any ice exposed at the surface can become extremely cold, potentially cold enough for nitrogen or methane to condense. Then, during summer, these volatile ices may sublimate, creating transient atmospheres or redistributing material across the moon's surfaces. The recent discovery that several of Uranus's moons might harbor subsurface oceans adds another dimension to the seasonal story. If these oceans exist, they're likely insulated enough that seasonal changes wouldn't affect them much. But any exchange between the oceans and the surface might be modulated by the seasonal cycle. During the long winter, any cryovolcanic activity or surface ocean communication might slow or stop. During summer, increased solar heating might allow water or ammonia-rich fluids to reach the surface more easily, potentially replenishing material to the magnetosphere. This brings us full circle to the story of Uranus's existence. It is a world shaped by catastrophe, ruled by patience, and defined by extremes. The same impact that condemned it to tumble sideways also created the conditions for one of the most unusual planetary environments in the solar system, a place where day and night are measured in decades, where seasons span human lifetimes, where chemistry happens in slow motion during the long sleep of winter before accelerating during the brief awakening of summer. The planet teaches us that time is relative, that the rhythms we take for granted on Earth, the daily cycle of day and night, the annual progression of seasons, are not universal constants, but local accidents of planetary formation. On Uranus, patience is not just a virtue, it's the fundamental tempo of existence. The planet moves through its orbit with a kind of serene indifference to human timescales, unfolding its mysteries at a pace set by orbital mechanics and the distant tug of the Sun's gravity. Let us now consider humanity's relationship with this distant world and what the future may hold for Uranian exploration. Since its discovery in 1781, Uranus has occupied a curious position in our collective imagination. It lacks the commanding presence of Jupiter, the visual splendor of Saturn, the romantic allure of Mars. It doesn't inspire the same fear and wonder as the Sun or Moon. Uranus is the forgotten giant, the planet that casual astronomy enthusiasts often overlook, the world that even dedicated skywatchers struggle to find. And yet, to planetary scientists, Uranus represents one of the most important targets for future exploration. Ice giants like Uranus and Neptune may be the most common type of planet in the galaxy. Recent exoplanet surveys have revealed that planets with masses between 10 and 50 times Earth's mass, what we call mini-Neptunes or super-Earths, are incredibly abundant around other stars. Understanding how ice giants form, what processes drive their atmospheres, how their magnetic fields work, and whether their moons can support habitable environments has implications far beyond our own solar system. For nearly 40 years, our only close-up data from Uranus came from Voyager 2's brief flyby in January 1986. That single encounter, lasting just a few hours, provided humanity's only detailed look at the planet, its rings, and its moons. Every image we have of Uranian surfaces, every measurement of the magnetosphere, every observation of cloud features from close range comes from that one precious flyby. And now we know that Voyager arrived during highly unusual conditions, catching Uranus in the aftermath of a solar wind event that compressed the magnetosphere and may have suppressed normal atmospheric and magnetospheric behavior. It would be as if alien astronomers visited Earth for a few hours during a massive solar storm and assumed the extreme space weather conditions they observed represented Earth's typical state. The planetary science community has long advocated for a return mission to Uranus. In April 2022, the United States National Academies of Sciences, Engineering, and Medicine released its Planetary Science and Astrobiology Decadal Survey for 2023 through 2032. This influential report, which helps guide NASA's priorities for the coming decade, designated a Uranus orbiter and probe as the highest priority flagship mission for the next decade. The report made the case compellingly. Uranus and Neptune remain the least explored planets in our solar system. The ice giant class of planets requires dedicated study to understand planetary formation and evolution. The Uranian moons may harbor subsurface oceans, making them potential habitats for life. The planet's bizarre magnetosphere, extreme seasons, and dark ring system all pose fundamental scientific questions that cannot be answered without detailed, long-term observations. Following this recommendation, NASA began preliminary studies for a Uranus mission. The current concept envisions a spacecraft launched in the early 2032, using a gravity assist from Jupiter to reach Uranus in the early 2040s. The spacecraft would carry an atmospheric probe that would separate from the orbiter before arrival and plunge into Uranus's atmosphere, measuring its composition, temperature, pressure, and wind structure as it descends. The probe would provide the first direct measurements of a major planet's atmosphere since the Galileo probe entered Jupiter in 1995. The orbiter would arrive at Uranus and enter a long-term orbit around the planet, studying the entire system over multiple Earth years. This would allow scientists to observe how the planet changes as it progresses through its seasons, how the moons respond to different illumination conditions, and how the magnetosphere behaves under various solar wind conditions. The orbiter would carry a suite of cameras to image the planet, rings, and moons in visible and infrared wavelengths. Spectrometers would analyze the composition of the atmosphere, ring particles, and moon surfaces. Magnetometers and plasma instruments would map the magnetic field and characterize the magnetosphere. A radar sounder might be included to penetrate beneath the surfaces of icy moons and search for subsurface oceans. Multiple close flybys of the major moons would allow detailed mapping and compositional analysis. The mission would address fundamental questions about Uranus's interior structure by precisely measuring the gravitational field and how it changes with position. These measurements would constrain models of the planet's internal layering, helping determine whether the mantle is truly stratified and whether a diamond-rich layer exists at depth. The spacecraft would also be able to measure the planet's magnetic field in detail, mapping its structure and determining how it's generated. This would provide crucial tests of ice giant dynamo theory and help us understand why Uranus's field is so different from Earth's. One of the most exciting prospects for a Uranus orbiter involves the moons. If Ariel, Titania, Oberon, or other moons indeed harbor subsurface oceans, the orbiter would be able to detect them through several methods. Induced magnetic fields created as the moons move through Uranus's magnetosphere would reveal the presence of electrically conducting layers beneath the surface. Precise gravity measurements during close flybys would constrain the moon's internal structures. Surface geology could reveal signs of cryovolcanism or ice tectonics driven by subsurface water. Europa, Enceladus, and Titan have taught us that subsurface oceans are not rare in the outer solar system, and the possibility that smaller, colder worlds like Uranus's moons might also harbor hidden seas is tantalizing. The existence of liquid water in contact with rock creates environments where chemistry interesting to life can occur. While the Uranian moons would be cold, dark, and isolated, the basic ingredients for habitability might nevertheless be present. A Uranus orbiter would help us understand not just one planetary system, but an entire class of worlds throughout the galaxy. The scientific return would be transformative, finally bringing Uranus into proper focus after more than 2 centuries of telescopic observation and 4 decades since humanity's only visit. However, significant challenges remain. The mission would be expensive, likely costing several $billion over its development and operational lifetime. The flight time is long, at least 12 to 13 years from launch to arrival, even with a Jupiter gravity assist. Once at Uranus, the spacecraft would operate nearly 3 billion kilometers from Earth, where sunlight is weak and communication times stretch to hours. The cold environment poses engineering challenges for spacecraft power and thermal control. Nuclear power sources would be essential, as solar panels become ineffective at such distances from the sun. Most critically, the mission faces competition for resources and attention from other compelling scientific priorities, including missions to search for life on Mars, explore ocean worlds like Europa and Enceladus, and study the outer reaches of the solar system. Nevertheless, the momentum is building. The Decadal Survey's strong endorsement has focused attention on Uranus. Preliminary studies are underway. Technology development for key spacecraft systems is progressing. If funding and political support materialize, a Uranus orbiter could launch in the early 2030s and arrive in time to observe the planet during its southern hemisphere's summer solstice around 2066. This timing would be scientifically ideal, allowing comparisons between Voyager's observations during southern summer in 1986 and modern observations at a similar seasonal point 80 years later. Beyond a dedicated orbiter, other opportunities for Uranus science continue to emerge. Ground-based telescopes are more powerful than ever. The James Webb Space Telescope has already begun observing Uranus with unprecedented infrared sensitivity, revealing details of the ring system, atmospheric features, and the growing polar cap with clarity impossible from Earth. As Webb continues its mission over the coming years, it will provide a long-term monitoring capability that can track seasonal changes and potentially discover new moons and ring features. The next generation of extremely large telescopes now under construction, including the 30-meter telescope and the extremely large telescope, will provide even sharper views once they begin operations in the coming years. These instruments, with mirrors tens of meters in diameter, equipped with adaptive optics to correct for atmospheric distortion, will be able to resolve features on Uranus and its moons approaching the detail visible in Voyager's images from nearly 40 years ago. Uranus has also entered popular culture in ways both serious and humorous. The planet's name, admittedly unfortunate in English, has long been the subject of jokes and awkward pronunciations. Some astronomers advocate for adopting the classical Greek pronunciation, which places the emphasis on the first syllable, making it sound like Uranus rather than the more problematic alternative. Yet despite the juvenile humor, there's genuine public interest in the ice giant. Documentary programs, educational videos, and science communication efforts increasingly highlight Uranus as one of the solar system's most bizarre and misunderstood worlds. Each new discovery, from bright storms to the recent magnetosphere findings, generates headlines and public attention. The growing recognition that ocean worlds might exist throughout the outer solar system, including potentially at Uranus, has elevated the planet's status from cosmic curiosity to potential abode for life. Now, as the journey nears its end and the night deepens around you, let us return once more to that central mystery, the question that gave this exploration its title, the frozen giant that sleeps for 42 years. We've traveled through the history of Uranus's discovery, explored its bizarre axial tilt and the violent collision that likely caused it, examined its frigid atmosphere and possible diamond-rich interior, visited its literally named moons and dark rings, and contemplated humanity's future missions to this distant world. Through all of this, the 42-year sleep has been our guiding thread, the peculiarity that makes Uranus unique. But now, having seen the complete picture, we can appreciate that Uranus doesn't truly sleep. The term was always metaphorical, a way of capturing the strange seasonal rhythm that rules this world. What actually happens during those 42 years of polar darkness is not sleep, but transformation. The chemistry shifts. The atmospheric circulation reorganizes. Energy redistributes through the planet's thick atmosphere in slow, patient currents. The hemisphere enters a different mode of existence, not inactive but operating under different rules, driven by different energy sources. It's less like sleep and more like a prolonged winter hibernation, where life slows but never stops. And when the long night ends and sunlight returns, the awakening is genuine. Photons that haven't touched that hemisphere in 4 decades suddenly arrive, carrying energy that drives chemical reactions, warms the atmosphere, and powers the return of storms and clouds. The polar region brightens as hazes accumulate. The planet transforms slowly and steadily from its winter configuration into its summer state. This seasonal transformation, happening over decades rather than months, reminds us that our human perspective, our Earth-centric view of how worlds should behave, is limited. We evolved on a planet with moderate axial tilt, orbiting at 1 astronomical unit from the Sun, rotating once every 24 hours. These parameters shaped our biology, our cultures, our intuitions about time and space. When we encounter a world like Uranus, where the seasons last longer than most human lives and the planet rotates on its side, our intuitions fail. We describe it as sleeping because our minds struggle to process existence on such a timescale. But to Uranus, if a planet could possess awareness, this is simply normal. The 42-year cycle is not strange or unusual. It's the fundamental rhythm of existence, as natural to Uranus as the 24-hour day-night cycle is to Earth. The planet's atmosphere, magnetosphere, and moons have all adapted to these rhythms. The shepherd moons orbit the rings with perfect regularity. The atmospheric winds flow according to patterns set by Coriolis forces and temperature gradients. The magnetic field tumbles as the planet rotates, creating its chaotic magnetosphere. Everything works according to physical laws that care nothing for human expectations. This is perhaps the deepest lesson Uranus offers. The universe doesn't conform to our expectations. It simply is. Physical law operates the same everywhere, from the crushing depths of Uranus's interior, where water becomes supersonic ice and carbon crystallizes into diamonds, to the gossamer ring particles tumbling in the planet's gravitational embrace, to the frozen surfaces of distant moons harboring possible oceans beneath kilometers of ice. Gravity, thermodynamics, quantum mechanics, electromagnetism, all the fundamental forces and principles that govern reality apply equally to every corner of the cosmos. The strange becomes familiar once we understand the principles at work. Uranus's 42-year seasons are not mysterious once we know the planet's axial tilt and orbital period. The math is straightforward. The planet's orbit takes 84 years. Half that orbit equals 42 years. During one half, the North Pole points generally sunward. During the other half, the South Pole does. The geometry is simple, even if the consequences are profound. This is the beauty of science, the way it takes the inexplicable and renders it explicable, not diminishing the wonder, but deepening it by revealing the elegant principles beneath. We stand now at a unique moment in history. For the first time, we possess the technology to truly explore ice giants. We have spacecraft capable of surviving the journey to the outer solar system and operating for years or decades in that cold environment. We have instruments sensitive enough to detect trace chemicals in atmospheres, map magnetic fields in 3 dimensions, and image surfaces with meter-scale resolution. We have theoretical frameworks sophisticated enough to interpret the data and extract deep insights about planetary interiors, atmospheric dynamics, and moon evolution. And we have the motivation, the recognition that ice giants are a crucial piece of the planetary science puzzle. The decision to send an orbiter to Uranus is not merely scientific, it's philosophical. It represents a choice to prioritize knowledge and understanding, to invest resources in learning about our cosmic environment rather than accepting ignorance. It's an acknowledgement that we are a curious species, driven to explore and understand, and that this drive is valuable in itself beyond any practical applications. As you drift towards sleep, wherever you are in the world right now, consider the light reaching your location. Perhaps it's daytime where you are, and sunlight streams through windows, illuminating your surroundings with the same light that left the sun 8 minutes ago. Perhaps it's nighttime, and the only light comes from artificial sources or the distant stars and planets scattered across the sky. If you looked for Uranus in the night sky, knowing exactly where to point your telescope, you would see it as a tiny disk, pale blue-green, shifting slowly against the background stars. The light reaching your eye would be 2.5 hours old, having bounced off Uranus's atmosphere and traveled across the solar system to find you. In that moment, you would be directly connected to the ice giant, participants in the same universe, sharing the same physical laws. The same photons that reveal Uranus to you would, if directed differently, reveal you to Uranus. The observation works both ways. This symmetry, this reciprocity, underlies all of astronomy. When we observe the cosmos, we are not separate from it. We are part of it, made from the same elements, forged in ancient stars, governed by the same forces that move planets and shape galaxies. Uranus, the frozen giant that sleeps for 42 years, has been our companion tonight on this journey through the outer solar system. We've seen how its discovery expanded human knowledge, how its unusual properties challenged our understanding, and how its future exploration promises to revolutionize our comprehension of planetary systems throughout the galaxy. The story of Uranus is ultimately a story about change and patience. The catastrophic impact that tilted the planet billions of years ago set it on a path different from any other world in our solar system. That single event, lasting perhaps hours or days, determined the planet's character for the following 4.6 billion years. The consequences of that ancient violence still manifest in the seasonal cycles playing out today, in the awakening northern hemisphere and the darkening south, in the tumbling magnetosphere and the dark rings. Every world carries its history within it, written in geological features, atmospheric composition, and orbital characteristics. Uranus's history is particularly dramatic, a reminder that the early solar system was a place of spectacular violence, and that planetary systems emerge from chaos through gradual organization over billions of years. As the coming decades unfold and new missions launch toward the outer solar system, Uranus will finally receive the attention it deserves. The ice giant will yield its secrets to patient observation and sophisticated instruments. We will learn what lies beneath those clouds, whether the moons harbor hidden oceans, how the magnetosphere behaves under normal conditions, and how the seasonal cycle influences every aspect of the planet's behavior. Each discovery will be a gift, a piece of cosmic knowledge won through ingenuity and persistence. Thank you for joining this exploration tonight, for lending your attention to a world that few people think about and fewer still understand. As you close your eyes and let the day's concerns dissolve, carry with you the image of that distant ice giant rolling through space, patient and eternal, cycling through its seasons with the same certainty that governs the stars themselves. Sleep well, dream deep, and know that the universe continues its ancient dance, whether we watch or not, somewhere far above, beyond the reach of our atmosphere, beyond the Moon and Mars, beyond Jupiter and Saturn. Uranus tumbles onward, its northern hemisphere growing brighter year by year as summer approaches, its secrets waiting for the day when humanity finally returns to explore this frozen giant in all its strange and wonderful glory.